Hi all, welcome to the Visual Recognition tutorial at ECCV 2020. My name is Georgia and I'm a research scientist at Facebook AI Research. Today I will talk about scene and object understanding in 3D. In 2D, visual recognition has witnessed tremendous progress. We've built systems that can recognize and localize all objects in a scene and even parse their pose. This video shows the output of a panoptic segmentation system, mask CNN, and dense pose, all developed by my colleagues at FAIR. But despite groundbreaking advances, current object recognition systems assume the world is 2D, and predictions are made on the 2D plane. These systems completely ignore the fact that the world is 3D and that objects extend beyond the 2D grid. Naturally, one might wonder why we care to understand the 3D properties of the objects in the scenes around us. Other than advancing the perception ability of computer systems, 3D is relevant for a vast variety of applications, such as AR/VR, robotics, and self-driving cars. When moving to 3D, an important decision needs to be made regarding the representation that will capture the 3D object or scene properties. There is a variety of such representations, and they all come with their pros and cons. Voxels capture a scene with a 3D dimensional grid. They're conceptually simple to use and integrate well with tensor libraries like PyTorch. However, they don't scale efficiently to higher resolutions. Point clouds represent a scene as a set of 3D points. They can efficiently capture fine structures, but they don't explicitly represent surfaces. Extracting a surface requires post-processing, as shown in this image here, which replaces each point with a mesh sphere in order to visualize the point cloud. Meshes represent scenes as a set of vertices and faces. Meshes are the standard representation for graphics and integrate well with rendering engines. Meshes can capture shape efficiently and are also easy to texture. But since they are graphs, they require a bit more work when processed by neural networks and tensor-based libraries. Signed distance functions capture shapes by mapping each point in the 3D space to its distance from the surface. They're not limited by resolution, but post-processing is required in order to extract shapes. Also, when SDFs are used to fit a set of target ground-truth shapes, those need to be watertight. Now going back to object understanding, in 2D we have built models such as mask/CNN that take as input a single image and output object labels and instance masks. And we have achieved this by training on pairs of images and 2D annotations. We enhance the recognition capability of mask/CNN to additionally predict 3D object shapes, and we achieve this by training on pairs of images and 3D annotations. Our system, called Measure-CNN, presented in ECCV 2019, takes as input a single image. It recognizes and detects all the objects in the image with 2D bounding boxes and instance masks. And it predicts the object's 3D shapes in the form of meshes. To capture the varying topologies of object shapes, we predict intermediate 3D voxels, which are refined to produce the final mesh predictions. An overview of Measure-CNN is shown in this figure. We build on mask/CNN that detects and recognizes all objects in the 2D plane. We add our voxel network, which predicts the voxelized object shape. Voxels are great because they can easily capture instance-specific shape topologies by merely turning occupancies on or off. However, they're bad at capturing fine details and are coarse. These coarse voxelized predictions are refined by our mesh refinement branch, which learns to deform the vertices with a sequence of graph convolutions. The final output is a refined mesh of each detected object in view coordinates. Defining loss functions for meshes is not straightforward because the same surface can be represented by different mesh topologies. So how can we define a loss between a predicted and a ground truth mesh? The idea is simple. We convert the meshes into point clouds by sampling points on the surface of the mesh, and for each face we sample number of points proportional to the area of that face. For the target mesh, we can sample points offline. But for the predicted mesh, sampling happens online and needs to be differentiable. We compare the 2 point clouds using chamfer distance. Chamfer distance is the sum of the altitude distance to each point's nearest neighbor in the other set. The chamfer distance is 0 if and only if for each point in the first set there is a point in the second set with altitude distance of 0, and vice versa. Minimizing solely the chamfer loss results in meshes that are not smooth and far from pretty, as shown in the second column of this figure. To enforce smoothness, we need to apply mesh regularizers, which eliminate phase intersections and irregularities. Smooth meshes are important if you want to use them for downstream applications such as texturing and rendering. We train Measure CNN on Pix3D, a dataset of images and aligned mesh shapes. Measure CNN is able to detect and predict object shapes from real-world complex scenes under viewpoint and appearance variations. To measure performance, we adopt the detection metrics used in object detection, namely Box AP and Mask AP, which measure the area under the precision recall curve at an intersection of reunion of 0.5 and above. For 3D shape, we define Mesh AP as the AP at a harmonic mean, or else known as F1, of 0.5 and above. Under that setting, a prediction is correct if and only if the correct class is predicted, the F1 score is above 0.5, and the prediction is not a duplicate. On Pix3D, we evaluate Measure CNN under 2 splits. First, we randomly split Pix3D into a train and test set. In this random split, 3D models can appear under novel viewpoints on both the train and test set. We compare to competing baselines, including a model which only makes voxel predictions without refinement, and mesh models which deform an initial sphere mesh, and show that Measure CNN outperforms them by a large margin. In the second and hardest setting, we split the dataset such that the test set contains novel shapes not seen at train time. To make this more clear, our split for chair might include kitchen chairs and armchairs at train time for the chair category, while in the test set, it will include novel chair shapes such as stool. This is indeed a harder setting, and performance drops significantly as expected, yet Measure CNN outperforms all baselines by a significant margin. We're glad to see the community working on this direction since our paper came out in ICCV 2019. In this ICCV 2020 project by Kuo et al., the authors learned a cat retrieval model to perform this task. Comparison with retrieval-based methods is a question we get a lot, and now we have some answers. For generalization to novel views, as in the first setting, retrieval can work quite well. But for generalizing to novel shapes, like in the second and hardest setting, a model that generates meshes, like Measure CNN, still does better. Measure CNN requires pairs of image and 3D annotations. But 3D annotations are hard to get compared to 2D. So can we predict 3D shapes without 3D supervision? To infer 3D shapes without 3D supervision, differentiable rendering can be used to project 3D back to 2D in a differentiable manner. Differentiable rendering was covered in the previous tutorial talk on PyTorch 3D by Nikhila Ravi. However, there is shape ambiguity when learning to predict shapes from a single image. Infinite 3D shapes can explain the same 2D image. For example, consider the input image on the left. There is infinite shapes that can explain the input image, 2 of which are shown in the second and third column. To overcome this ambiguity, we assume a 2-view training setup. At train time, our model, given an input image, predicts the shape of the object in view coordinates and renders its silhouette using differentiable rendering, which is then compared to the ground truth. The shape is transformed with a known transformation of the second view, and its rendered output is compared to the corresponding ground truth. This model uses only 2D supervision. It assumes object silhouettes for silhouette-based rendering, or the original textured views for texture rendering. And of course, it assumes that the model has access to 2 views of the same object at train time. At test time, the network is able to predict the object's shape in view coordinates from a single image. We conduct experiments on the ShapeNet dataset and the R2N2 benchmark, which consists of 13 categories and hundreds of thousands of images. This dataset is synthetic and images are clean, with objects in their center with no occlusions or clutter. It is very far from the complex scenes we see in Coco. However, it allows us to benchmark and compute metrics and thus quantitatively compare to previous state-of-the-art approaches such as SoftRAS. For the image encoder, we use a ResNet50. For the shape network, we experiment with various architectures inspired by recent advances in supervised prediction. First, we try a popular model for shape prediction, which uses a sequence of fully connected layers to predict the offsets for each vertex, which are then used to deform a sphere template. We call this model Sphere FC. Inspired by Measure CNN, we also experiment with a more geometry-aware architecture. This model makes a 3D shape part of the network architecture by allowing it to pull features from a backbone based on its geometry, and perform geometry-specific computations by graph convolutions. This results again in offset predictions for each vertex of a sphere. We call this model Sphere GCN. Note that this model follows our Measure CNN architecture quite closely. We compare to the previous state-of-the-art in differentiable rendering, SoftRAS, presented in ICV 2019. We replicate their experimental setup, which uses a Sphere FC model, deforms a small sphere of 642 vertices and 1280 faces, and renders at a 64x64 resolution. We see that PyTorch 3D performs better than SoftRAS. However, absolute performance is not good enough. The more geometry-aware Sphere GCN model performs much better under the same setting. To push performance even further, we deviate from the SoftRAS setting and render at higher resolutions. We notice that both Sphere FC and Sphere GCN improve with higher rendering resolution, showing that resolution is important when using renderers, even for a simple dataset like ShapeNet. This emphasizes the need for rendering pipelines to gracefully scale to higher resolution, and PyTorch 3D does. From these experiments, we observe that PyTorch 3D works great. We also note that Sphere GCN, inspired by Measure CNN, is a superior model for this task. This is also shown qualitatively. Consider these input images at test time. Sphere FC captures global pose and semantics, but it cannot capture specific shape details to accurately reconstruct the objects. Sphere GCN makes more accurate predictions, and note that both models learn to deform the same sphere. This validates the use of geometry-aware network architectures. So far, we've been sticking to a small sphere template of only 642 vertices and 1280 faces, following the experimental setting of SoftRAS. Thanks to PyTorch 3D and its scale efficiency, we can go bigger than that without any slowdowns in training or inference speed. We train a Sphere GCN variant that deforms a larger sphere. We call this variant High-Res Sphere GCN. Now the shape has more degrees of freedom to try to simulate the shape topology, and our model does that while maintaining a good computational throughput. The predictions from High-Res Sphere GCN look incredibly accurate, and it's clear that it tries to do the best with the constraint it has, which is deforming spheres. Putting everything into a single bar plot, we note that PyTorch 3D scale efficiency allows us to improve the initial SoftRAS baseline by a huge amount. To emphasize the good performance from our unsupervised models, we also compare to the state-of-the-art supervised Measure CNN, shown in pink. We note that the margin between supervised and unsupervised has reduced significantly. PyTorch 3D also offers support for texturing meshes. We can easily extend our models to predict RGB values for each vertex, which learn to predict the shape's texture from the input image. PyTorch 3D's modularity allows us to play with various shading functions, lighting, and other aspects of texturing, and all with pure PyTorch code. I will skip these results, but you can learn more about this in our codebase and our tech report. We can also train unsupervised point cloud models using PyTorch 3D's point cloud renderer. We adapt Sphere GCN and train a model that starts from a sphere point cloud. Graph convolutions are replaced by linear layers applied to pair point features sampled from the backbone feature map. We call this model point-align. Point-align performs great for shape reconstruction and further reduces the gap with supervised learning approaches. This is also proven by visualizations. Similar to meshes, we can add texture predictions and reconstruct object textures. The previous example showed how scale-efficient tools can help improve the state-of-the-art by simply going bigger in resolution and size. But the use of 3D and rendering are not limited to shape predictions. There is a lot of cool applications to be unlocked by 3D reasoning, such as novel view synthesis. Here, from a single image of a scene, we want to produce images from different viewpoints. We use 3D reasoning and rendering for the task of novel view synthesis, an effort that was led by our amazing collaborator, Olivia, who is presenting her work in CVPR 2020. Of course, we're not the first ones to tackle this problem. A variety of methods have tried to synthesize novel views focusing either on synthetic and single object images or using stereo and ground truth 3D supervision. Our approach uses a latent point cloud. A feature network encodes an image and produces per pixel features. A depth network predicts depth for each pixel, producing a 3D point cloud with features assigned to each point. This 3D point cloud is transformed under the target viewpoint transform and rendered in the new view. The projected views are passed through a generator to produce the final image, while at train time a discriminator makes sure the output looks natural. At train time, the target predicted image is compared to the ground truth. This method uses only image supervision, original and target view, and assumes a transformation between the two views. There is no explicit 3D supervision for the scene. We focus on complex scenes from Matterport, Replica, and Real Estate 10K, which all contain walkthroughs of indoor and outdoor scenes. Experiments show the effectiveness of SynSyn compared to image-to-image approaches and methods that use latent voxels instead of point cloud representations. You can find more details on the performance and the benchmarks in our paper. Here are some visualizations of novel views at test time. Even though we don't supervise our network with any 3D information, nor do we force it to learn an accurate point cloud representation of the scene, the model is able to make reasonable point cloud predictions. In addition, we show zero-shot generalization to novel, higher fidelity datasets. And even to higher resolutions without retraining our model. To summarize, I presented ways to infer 3D shapes from 2D images, with or without 3D supervision. But 3D is not limited to shape reconstruction. It can be used as a latent representation for other applications, such as novel view synthesis. And to do all this at a large scale, efficient tools are needed, like PyTorch 3D, which has powered all the projects presented today. Thank you for watching, and if you have any questions, feel free to drop by our Q&A session.